All right. Hello, everyone. Welcome to Google DSC's at UQ's second lecture today. First lecture we did a little while ago. We did Google we did Introduction to Unix Command Line. And today we have the wonderful David Parrish giving an introduction to Golang. So give him a warm welcome. And remember to leave any questions you have in the YouTube chat, and we'll be sure to answer them. All right. Take it away.
Cool. Hi, everyone. I'm Dave. I've been at Google for 13 years now. I've been in the IT industry for 25 years or so. Turns out I love Go. Having done lots of different programming languages and then switched to Go, it is absolutely fantastic. And yeah, Hamish asked if I could give an intro. So hopefully it will be a reasonable level of skill required to understand. But what I'm going to do is quickly run through the basics of the language structure and then get into some of the fun things that Go offers. So I'm doing this with the idea that everyone has some knowledge of some different other programming languages. I'll make reference to C in a pile of things just because of the similarities. Feel free to watch the video again. So just to start off with, Go is a compiled, strongly typed language. It is extremely strongly typed. It makes C look weak typed. But one of the cool things is it compiles really, really quickly. So play.golang.org is the site that I'm using now, which gives you a playground where you can type code in and have it run directly. And it takes seconds to compile and run that code. So just to starting off with, everything in Go is in a package. In this case, package main is the package that runs the code whenever you start your code. And it generally runs a function called main. So if you've looked at C code before, that kind of makes a lot of sense. Everything is divided into packages. So you've got packages for printing, which are in the FMT package. You've got functions for time management and time zones and that kind of stuff, which is in the time package. And similar to many other languages, package.function name will do whatever is needed by the particular thing. So in this case, we're just printing out hello UQ and using C-style printf bits, format strings, sorry. So yeah, if you've done C, that should look relatively simple, relatively familiar. So we can go slightly further than that. Packages do need to be imported before they could be used. So if you, for example, try and run something like print a random number and use something in the rand package, it should immediately give you an error saying undefined rand, good. We include the rand package and run it again, and it works beautifully. Oh, it's not rand, it's math rand. Brilliant, we've got a random number. So yeah, the import errors are quite reasonable. And one of the things that's really nice with Go is that because the language is so easy to compile and type check, it means that the code formatter is also running through the same compiler. So if you do something like hit the format button or go format at the command line, it will actually go and work out the imports that you need for the sort of basic stuff. It's pretty good at finding your own custom packages as well. So just like C, you have the ability to have structures, complex structures, nested structures, whatever you like. And the way you define them is with the type command. So different to most other languages, C included, you put the name before the type name. And that's because it makes the compiler and the lexer a whole pile simpler, which is one of the reasons it can be a lot faster. The language is very, very strictly defined. So we have a type, core scores. It is a struct, and it has 3 variables in it, class 1, class 2, and class 3, which are all of type float64, which is a 64-bit float. So in our main, we declare a variable using the var keyword. We call the variable myscores, and we say it is of type core scores. If you've done any object-oriented stuff before, the dot notation for setting particular bits is probably very similar to you. So we give you a score of 90 for the first class, 99 for the second class, and because we're terrible at it, class 3, we only get 3.1, and we run it. It's compiled and it gives you the output. interestingly, the output that it gives you can be used directly in the code to declare the variable as an initializer. Before we get to that, there is a slight shortcut that Go gives you, because this is kind of longhand. You get the := operator. So I can say, without having to declare var is a type course scores, I can say my scores is a something, and it happens to be an empty course scores. Not particularly useful on its own, but if you change it to use the package initializer, which is what was printed out before, then you can declare and set the fields of the structure with one command. If I wanted to, I could copy the output in, and it should still run. No comma, whatever, close enough. So that's all very interesting. You can see here we've got a function, func, so we can declare other functions with func as well. I'm running through this because this is hopefully very easy stuff. But we can do what you'd probably expect to do, which is create a function called average score, which adds up the scores and divides by the number and gives you a return. So the : will give you a variable which is typed to the return of whatever it is that you happen to be doing. So in this case, average score returns a float 64. So average will be a type 64, float 64. And yay, average score is 64. Skipping through because it's not particularly interesting. One useful thing here is that functions can have multiple return values. So this is often used because Go doesn't have exceptions. You return multiple values from a function to denote the return status as well as an error. So in this case, we extended it slightly. We've changed average score to passing score. So this takes a set of scores, or a course scores structure, and it returns both a float 64 and an error. So in this case, I say, work out the average. If it's below the passing score, which I've defined as 50, then don't return a value, but return an error of type new. And the errors package contains a few functions for creating and working with errors. And you can kind of think of them like exceptions in another language, except that they never bubble up. You have to actually use the value to do anything useful with it. So our main function changes. So we call passing score, and we assign the average variable and the error variable, which are created locally. Check the error. If the error is nil, which is the 0 value, so there is no error, then print out the score. If it's below the passing score, then error should not be nil, which means that it will print out the error itself. So if you run that now, and run, average score is 64, which is fine, but say we want to change the passing score to 65. We run it again, and we get a fail. Pretty simple stuff, but this is kind of how you do error handling in Go. One annoying thing is that assignments are not expressions in Go. So you can't do if average, error is passing score is less than nil or something like that. But Go does provide a shorthand, which is like this. So you can call your function, you can do the assignment, and then with a semicolon there, you can do the check to see whether it's successful or not. So this is really, really common standard Go error handling. Often, if you need to bubble it up, your function returns the same error. It can add to the error and return that, or it can crash or do whatever it is that you need to do. Okay, so I say Go is extremely picky and strongly typed. When it's extremely picky, it doesn't actually do any type conversion for you unless you specifically ask it to. So in the case, a simpler case, you've got your course scores as they were before, and I want to take a copy of that and give it extra credit. I want to add 2.5 to class 1. Unfortunately, I've declared extra credit as a float 32. Now, it could do the conversion for you. You can generally safely convert from a 32 to a 64-bit float. But because Go has made the decision that it will not do any type conversions implicitly. It will even fail with this, and it will give you an error that you've got mismatched types, float 64 and float 32. You can usually convert safely upwards, but many languages will let you convert safely downwards as well. So you could have a 64-bit int and convert it to a 32-bit int if it happens to be small enough. But then there's edge cases where it doesn't always work. Maybe it's different if it's signed. Maybe you didn't realize you're doing the conversion, and you could lose some values. So Go forces you to do a type conversion if you want to be able to use different types of variables. So I can convert that and explicitly say it's a float 64, and it works. It's not printing anything, but it didn't throw me an error anymore. One interesting thing is constants. Note there's no type specified there. Constants are high precision values. They're actually inserted during the compilation step. I could say passing score is an int, or it's a float, 32, or something like that. But if I just leave it as an untyped constant, then it can be used in place of any particular value. I can use it here. And that will take the type of float 64, because it's the same as just putting the number directly into the code. Hopefully skipping through more. Okay, so Go also has arrays and slices. So arrays and slices are kind of very similar, but with a couple of very important distinctions. So arrays have a fixed size and a fixed RAM allocation. So in this case, I'm declaring a variable called scores, which has a type of float 64 with 10 slots. This is actually the type of the variable. It's not a float 64 with a size of 10. The type is 10 float 64. It can only be passed to things that require a float 64 with 10 elements. It can't be resized. It can't be shrunk. You can't delete elements from it. You can just set them to values. But it does work, and your normal things that you would expect, you can get the len, you can get the individual values. It works as an array would in most other languages. It's not particularly useful, so generally what you use is what's called a slice. And a slice officially is a pointer to a chunk of an array. So I could declare a slice which is pointing to all of this scores value, or I could just declare a slice on its own, and a slice is declared similar to an array but without a size. Also interesting to note that now float 64 is a slice. It is not the same type as the array, even if it happens to have 10 values in it. It's very, very strongly typed in that way. You can do the normal things. You can add scores. You can do the length of scores. You can get values. You can do slices from particular ranges. So 0:1 will get you the first two elements, those kinds of standard things. If you've done any Python or even C array manipulation, it should all seem quite familiar to you. Now, when you're going through these things, Go only has a single looping operator, which is for. And for some examples of it, here is a function that does the average score. So the bottom stuff is the same, but what this does is very similar to a C for loop or a Java for loop or many other languages. It will start from 0. It will go until it is less than the length of scores, and it will increment I by 1 each time. So it has an init, a conditional expression, and a post statement for every iteration. Hopefully I didn't screw up the maths, and this is a basic average calculation. There's some interesting ones like divide by equals and plus equals, which are the equivalent of doing average equals average divided by len. It's just a shorthand version of the same thing. And hopefully, look at that, type conversion, float 64. Its length of scores is an int, and it's trying to do a float divided by an int, which doesn't work, but that does. So our average score is 60.05. Excellent, that all works. Because Go likes to be flexible, you don't need the parentheses around them, but you do need the braces for the actual function. You can leave chunks of this off. because part of it is worked out on its own. So in this case, you can say, I want to declare the int outside, and I can just do for I less than len scores. So it will start off with whatever it is before, which by default is 0, and it will continue doing that. And I've got the post expression here because why not? You could do it that way. You can go slightly further, just make sure that works. Excellent. You can go slightly further and remove it completely. So now you have an infinite loop. So there is no while function. There's no do while. You basically do all of it with different variations of the for statement. Infinite loops should go, yes, crash. It's smart enough to work out that it will never get to there. And crash. Good. That's what I like. Next step is there is a range operator as well. And this will become more useful later. But for an example, here is how you can use it. So the range operator will iterate over whatever it's given and give you the index and the value for each of the elements in there. Because Go is extremely picky, it will complain and not compile if a variable is declared and not used. So I don't need the index, I just need the score. So I replace it with another score and it should work. Go is very picky about this sort of thing. So any undeclared variables will fail. Any unused variables that have been declared will fail. Any packages that are imported will cause it to crash as well. You need to have really clean code for it to even compile, which I've got to say I like. It means that I don't get stuff breaking in production. Just like C and other languages, there is also a switch operator. I apologize in advance if I'm rushing through this, but there's some other more interesting stuff later. So the switch operator works similar to most other languages, with the distinction that there is no fall through like C. In C, you'd need a break there to stop it falling from this case to the next one. For some great reason, they just decided not to do that in Go, and it works brilliantly. So in this case, it does a switch. You can have a switch on a value, on a variable, but in this case, I can't do greater than equal to. I could do case 85, and that will only trigger that particular case when the value is exactly 85. In this case, I don't really want it to do that. I want it to do greater than. So you can just do switch, and then each particular case can have whatever you really need to. This could be different variables. Kind of looks terrible if you do that. It's going to be breaking. Also, this is using the short initializer form. So I'm creating the variable, and it is of type average score. Sorry, no, it's running the function average score, and I'm passing directly in 3 float values. I don't need to give them positions or anything. It just is smart enough to work it out itself. So no longer using the struct, just a slice of floats. And this will work with any number of elements, 10, 50, 90, 3, 100, 1000, whatever. Doesn't need to care that it's what length it is. It just works with any length at all. Another useful Go-specific function is defer. So defer lets you put in a statement which will run when the function that it's executing in exits. So Go is all lexically scoped. Variables only exist for the lifetime of the lexical scope they're in. But you can defer statements to run at the end of the function. So in this case, it's basically doing the same thing it was before, except that I'm deferring the print until later on. So if it runs through, it should calculate the average score. It will work out your grade. It will defer the print of the grade, and then it will print out the score. So at the end of it, you get the score first and then the grade at the end of that. So defer is usually used for cleanup, and closing of file handles and deletion of variables and those kinds of things. Go is a garbage collected, reference counted language. So you generally don't need to worry about freeing memory when you're done. But it's quite common to open a file handle, read from a file, and then defer closing of the file handle, because what it does is keep the open and the close together in your code, and you get used to seeing open and then immediately defer close, and then you do whatever you want with the file handle at that point, knowing that it will eventually be cleaned up and closed. Defer is very, very cool. Next basic chunk, Go has maps. Associative arrays in other languages. Hopefully everyone is familiar with this sort of form of thing, but you declare the map as a type. So this is the actual type of the grades variable. It is a map with a key of float 64 and a value of string. Again, very, very strict on the type safety of it. I could declare this as an int or an int32, because these are all integers. But then further on down, when it's looking through them, it'll be comparing the average, which is a float 64, against the value or the key, which is an int. Just gets nasty. So if it's float 64, it's all good. This is a terrible thing. Don't ever do this. But as a demonstration of how maps work, this is kind of it. So it loops through the grades, loops through these using the range operator. So it gets the index and the value, checks if the given score is above the index, which is this one here, and that hasn't already set. Maps are randomly ordered, so you can't iterate through the map in the order that you defined it in. So you have to do this sort of nastiness and say, well, I only want to set the grade if it's the highest one that I've set. Either way, it still works. I get a pass score. Nothing more interesting now. Okay, so Go doesn't have classes. Go has structs, and you can define methods on structs. In fact, you can define methods on any type that you like, including things like integer. You can't actually declare a method on an int, but you can declare a new type, which is basically an int, and then you can define your methods on that. So in the normal case, you define a struct. So I have my struct of type results, which has a slice of scores inside it. And then I define some methods on that struct. So the first bit is the receiver, which is the equivalent of this or self or other things in other languages. But it basically says, for this particular function, it's going to be attached to the results. It's going to receive a pointer of results. Yes, Go has pointers. They are reference counted, unlike C. They're not as bad as C. They're actually quite useful. But yeah, so average is a function or method on the results struct. It takes the results. It returns a float 64. And inside, because I've said R is the results object, your normal dot notation applies. So R.scores will give you this value there. Hopefully that makes sense. Same thing for grade. In this case, it's calling R.average. So it's calling the average method on itself. This is quite normal for object-oriented type stuff. In main, we declare the results. Now, because the struct receiver is a pointer, that means that we have to declare the results object as a pointer itself. So the notation for that is ampersand. So I'm creating a results structure, and I'm getting the pointer to that. It's slightly worse than that in Go, because the type of this is actually a pointer to results. It's not a pointer to a result struct. It is a pointer to results as a struct, or as a type. Nasty. And we just set the score and go, yay, everything works. Same thing as before. Hopefully everyone here is getting a pass, at least. Yeah, another interesting part of this is you may have noticed the capitals for the start of these. Go is very opinionated in the way that you should be writing code, and it's made some interesting decisions. One of them is that anything with a capital letter to start is exported from the current package. So if it was results with a lowercase r, that means that this structure would not be available outside this package. So it's uppercase R. Same thing with the fields inside it. If it's a lowercase, then that field is only accessible to things inside this structure, or even inside the package. But because I want to see it outside, it needs to be a capital. Same thing with functions. There is no concept of private and public functions. There are just lowercase ones, which are not exported, so you can't use them outside, or they're not even in the dictionary, or uppercase, and they're available outside. You get used to it. It does mean that you are generally required to follow the Go style in terms of how you format your code. You don't have arguments whether it should be camel case or snake case, because the language defines that camel case is the way that you have to do it, otherwise it won't be exported. So suck it up, princess. So Go also has interfaces which are similar to interfaces in other languages, but not quite the same. One of the key points of interfaces in Go is that you never say that you're implementing an interface. The interface just has a set of methods, and anything that implements those methods implicitly implements that interface. So, pasting more junk code, I've declared an interface here. So just like all the other declarations, it's a type. It's called generic results. It's got a capital G, so it's exported outside of this package. And it's an interface that has these particular methods. It's got an average method returning a float 64, and it's got a grade method returning a string. There's no such thing as operator overloading or function overloading, so a function called average will always return a float 64. It's quite common to see things like average int 64 and then average float 32 in lots of libraries, but it's quite simple. So the reason this is in capitals is because this is generally what you would export outside your package. You may not want people to see the internals of your structure. You just want to say you have a structure, some kind of structure. It implements the average and the grade function, and that's all that you can call on it because that's all the interface says that it is. Interestingly, the results here doesn't have to be a struct. This could actually be of type float 64 or slice of float 64. And as long as those methods are still tacked onto it, then it still implements the interface. So you're free to do whatever you like internally. You can change it. You can change it to disk-backed, memory mapped, or some kind of other complicated structure, whatever you like. It could be a database behind the scenes. As long as it implements those two methods, average and grade, then the code will function. And it's still considered to be implementing that interface. This is used very, very heavily in the standard library. The most common standard one is called stringer. So this is commented out because this is defined by the format package, but it's an interface called stringer, which says it just needs to have a method called string that returns a string. It seems simple, but what it means is that the print functions know how to convert anything that implements the stringer interface, which is to say it has the string function. So all I need to do is define the string function, and then it implements the stringer interface because I've done that, and it means that the format print functions automatically know how to do the conversion. So I can pass in the results structure directly as an object and tell it to format as a string, and it knows how to call the string function because it implements the stringer interface. There's some other useful ones. The IO libraries define a reader and a writer interface. So anything that has a write function or write method that has a particular set of arguments can be written to by any of the IO libraries. It can be a database handle, it can write to this terminal, it can write to files, it can write to cloud storage and all these sorts of things, as long as it implements that particular function. Same thing with read. you can declare a block of string in RAM and give it a read method, and then that can be passed to all the IO functions, including copying and printing and CSV parsing and whatever it is that you need to do, as long as it implements that particular interface. It's more complex than it looks, but it also simplifies things a whole lot. You never have to worry about what's going to use your object. You give it the functions that it needs, and it can be used anywhere that accepts those functions. It ends up with quite flexible code without having to do anything, and it kind of looks like magic. So we're 35 minutes in. That's the basics of the language structure. Now we get into useful things. So one of the great things of Go is that it is, from its namesake, it is cooperatively scheduled, highly threaded runtime, and it uses what they call Go routines. So if you've ever seen coroutines as a thing before, these are generally lightweight threads that are managed by the runtime, usually, not by the kernel scheduler. And so they are faster to switch between. There's less overhead. You get a much clearer sharing of RAM semantics. And so Go made Go routines as a first-level native object. So to use them, use the keyword Go, because why not? So in this case, we have our function just as before. We've got our average function. It does some calculation. The calculation in this case is very, very simple. Also note that it's doing the calculation on a type results, which is just basically a renamed slice of float64. It's not just renamed, it is an entirely new type, but it happens to be based on a slice of float64. So without that bit there, what you'll get is not used. So you get calculating average and then program exited. Because this is run from a Go routine, it immediately starts the Go routine, it runs in the background, but it may not get time to schedule and print out the output before this next function runs, and it exits the code. So it's never going to actually happen. So what we do is we add a sleep to it, run it again, and now it takes a second longer, but I get the calculating average from the main function, and then at some point this other Go routine will run, and it will run in the background, and it will be scheduled, and it'll be fast scheduled and fast switching in and out of it, but it'll run sometime in the background and then print out the average score. Because Go routines are extremely lightweight, it's really common to start Go routines for anything that will take some sort of computation time. There's a whole pile of libraries that help with scheduling and waiting for returns and waiting for groups of Go routines to complete and then passing error returns back and those kinds of things. But it's really, really common to spawn a Go routine every time you want to do something in the background. But this is terrible. I don't want to do a sleep at all. So we come to the second innovative feature in Go, which is channels. So channels are a typed conduit for passing information and for synchronization. It defines a new operator for using channels, but pasting in the code, we'll go for it. So starting from main, we declare a variable called ch. And by the way, Go style encourages variable names to, the length should increase with the size of the scope. So it's good to have single letter index variables because they're only used inside a very small scope. It's good to have a few letters for small function level variables. As soon as you start having global constants or package level constants, you want them to be long and descriptive names. It's good to have it well defined that you do want short variable names in some cases. So anyway, we create a channel variable. We use the make function, which is the built-in that creates some particular objects, including channels. And we say we're making a channel of float64. So what this means is the channel is now created It's empty, there's nothing on it, but it can fit objects that are float64s onto that channel. Then I call results.average in the background because I use Go, and I pass it the channel that it's going to return information on. So if we go up to average, the definition has changed slightly. It now takes a channel of float64s, and it happens to be called CH. It doesn't have to be the same name, but it is for consistency. CH is a good name. It doesn't need to take the results because that's already taken as the receiver for the method. But it does the same average calculation and then uses the channel operator to write the value to the channel. So it adds the score for each one, and then what gets written is the total divided by the length, so normal average calculation. So this does a few interesting things. This will block until there is something ready to read that value. So in this case, this function will block at this particular write until it gets to the point further down below where it tries to read from the channel. So in this way, channels are used for synchronization. You can declare a size for the channel. So if I say, instead of make chan float64, I make chan float64 500, that declares that the channel is now buffered with 500, or space for 500 float64s in it. So if I do that, then this line here won't block. It will execute immediately and put one entry into the channel, and then this will still execute at the right time down here. It does work. It takes a lot of practice to get used to channels, but they are extremely powerful when they're used for the right situation. This is obviously the wrong situation, but this is just demoing what they're capable of. For a slightly more complex way, channels are also used for synchronization between Go routines. Why do we need to do that? So they can be used, they're open until they're closed, and the close itself can be a signal which is used to indicate that there's no more work to do. So we changed this function slightly here. So it's no longer calculating average. It's calculating some numbers. So first thing it's doing is calculating the average and writing that value to the channel. And then it's calculating the standard deviation. Hopefully that's relatively correct standard deviation maths. I'm not good at it. And then it's writing that value to the channel. And then last thing, it's closing the channel, which basically says there is no more work to do. You've got all the values that is ever going to be produced. So in the main function, we declare the channel the same as before. We start running the calculation in the background. And then we use the range operator, which was seen before, to get values off the channel until the channel is closed. You can do a for loop where you try and read a value and then check the return status from the read and work out whether the channel has been closed. Or the range operator just does it for you and then works out when it's closed. So if you run that, you get two numbers out of it. Average is still 64.05, and now the standard deviation is 43.22. That seems roughly right to me. I don't know. Maybe I got the maths wrong. But what you're doing here is you're running something in the background with very, very little effort. You don't have to deal with threading libraries. You don't have to deal with mutexes around critical sections or around variables that you're reading and writing to. There is support for mutexes, but generally you pass information around with the channel. So you're very explicitly saying you do whatever you like. The input and output from this Go routine will only be through a channel, and they are completely thread safe and useful for a pile of things like this. Channels are cool. When I started writing this talk up, passed it around my team at work, and multiple people in the team said, I've been using this for a year and still haven't got the hang of channels. They look very similar here, but there's interesting edge cases. Now, this is not generally the way you do it in idiomatic Go. What you tend to have is a producer-consumer type method. And I'm just going to paste in this chunk before we get to the next bit of it to talk through it. So this is the way you would normally do it in Go. What you do is you have the function that you're calling maintain the life cycle of the channel. So it is the only thing that will write to it, and it's the only thing that will close it. So the first thing you do is make a channel, and then you spawn off a Go routine, which will do the work of the function, and then you immediately return the channel. So when you call this function, the only things that get run is make the channel and then return the channel. The Go routine scheduler will then pick this up and say, okay, I'm going to run this in the background. And it is very clever on when it runs the Go routines. It has ready lists and busy lists and knows which functions and which Go routines are waiting for particular things. So if you have multiple functions that happen to be waiting for a channel, it will pick one at random. It will pick one that's ready for receiving. It will switch to it without invoking the kernel scheduler, and it will be nice and fast and all the things you want. But this is very idiomatic Go for the producer type method. Create the channel, do some work, return the channel. So it's good because nothing else has to close that function. Nothing else has to know the lifecycle. So this was part of a bigger chunk. So we've got our average function, which should not do that. And we have our standard deviation function. So they're separate functions now doing separate things. It still has to calculate the average because you still need the average to work out the standard deviation. But the average function will write a single value a single value to its channel, and the standard deviation function will write a single value to each channel. So there are two separate channels, one for each of them. They are closed using the defer function, which is important. It kind of keeps the creation and the destruction of the channel close together. But it means that even if this function here returns an error at some point, it crashes, it does something that it's not supposed to, it will always call the close function when this function returns, so when the Go routine ends. And I thought that was going to sleep. Okay, so that's completely the wrong code. Anyway, I got halfway through that and didn't paste it in. Oh, that's better. Okay, so what this is doing differently now is we've got the two functions and it's creating two channels. So there's a channel to get the average value and there's a channel to get the standard deviation value. I actually forgot something. Sorry. Paste. Okay, because these are quick functions, I've added in a random sleep. So each one will sleep a random of up to 200 or 100 milliseconds, just so they can demonstrate the difference. So this is running both of these. It doesn't need to call Go here because the first thing the function does is spawn off a Go routine in the background after it creates the channel. So this creates an average channel and a standard deviation channel. You don't have to know that this is doing some work in the background. It could be all in the foreground. It could be in the background. It could be a combination. You really don't know. All you know is that it's returning a channel, and at some point, you're going to get some values off this. Next part is it actually uses a new operator called select. Select is an important one because it lets you wait on multiple channels and basically get the first one that's available. So in this case, we're racing average and standard deviation. It's going to select on both of them. One of these is going to run. So it's either going to get the value from the average channel or it's going to get the value from the standard deviation channel. It's going to ignore the others because it's going to crash. So if we run this once, get the average, good. Run it again, get standard deviation. Because each one is sleeping a random amount of time, it's kind of random which one it's get, but it's basically going to erase this. We use this heavily for one of the common things we'll do is have two separate databases that have the same data. And for reliability, you could query one, and if it fails, query the next one. Or you send the same query to both, and you use whichever one comes back first. So this kind of structure is so common. Useful. Anyway, that was my allotted 50 minutes to go over a whole pile of stuff. I know I went through it very quickly. I apologize. A lot of this was taken from the Go language tutorial on the website. The cool thing with the tutorial is that it uses the playground as part of the tutorial, so you can edit the code, you can run the code, you can try stuff during the tutorial. It's cool. So was leaving 10 minutes for questions, if there are any, Hamish or James.
All right, seems we've got a few more, but how much more, David, do you have? Because we probably have a bit of time to keep going if you'd like.
That was pretty much it for the code that I'd written.
Okay, awesome. No worries. Well, I got a question here from Nicholas Lambourne. You ready to go?
Sure.
All right. So high-level languages like Python often have commonly used functions like print in the default namespace. Is there some advantage, e.g. speed, to requiring an explicit import for this kind of thing?
I don't know that it is. I don't know that it's for speed. I think it's more for cleanliness of the API. So things like make, which is used up here, make Jan. Make is a function in the global namespace, but it's actually part of a built-ins package. The entire standard library, including a pile of the language itself, is defined by the language itself. It's kind of weirdly self-hosting. It's just got some changes to make those built-ins be exported into the global namespace. Yeah, for cleanliness, everything is in a package. It's one of those things that if you make the decision that like you're going to be extremely strict on type safety and you're going to be extremely strict on package safety, it makes the language and the compiler a lot simpler not to have to bend those rules at any time. Hopefully it's a reasonable answer.
Seems pretty good to me. All right, I got another one from Magno here. If two Go routines belong to the same thread, do they get run in parallel, or does the scheduler allocate time slices so that only one Go routine can run per time slice?
Okay, so it's an M to N scheduler. So only one Go routine will run per processor or per processor core. And it does some nasty stuff to work out whether or not it's running on real cores or fake cores. You generally don't have to worry about it. You can run all the stuff with Go routines. You can have thousands of Go routines running, and you can set the maximum number of cores to use to 1, and it will still work as expected. So it will still time slice out the Go routines as it needs to. If you've got more cores, then those time slices will be longer because it's got more cores to run against. It's extremely cooperative, and it's designed around the fact that you should be making Go routines for any background work instead of the callback hell that you get from things like JavaScript, where everything runs through an event loop, which then calls something else on an event loop. You tend to have clear linear code running in Go routines. Effectively, there's almost no overhead to running a Go routine.
All right, not bad, not bad. One more here from Gareth, trying to be a bit funny. Does Go have generics at all?
No, it's coming, maybe. It's been in the works for years. Originally the authors of Go didn't want generics, and interfaces were a close second. Interfaces, so all of the arguments for generics, there's a lot of valid ones that interfaces will do just fine for. It keeps the language simpler. Having done a pile of work in C++, the meta compiler is abused by so many things because generics make things flexible and powerful, but you end up with some awful language. If you've ever looked through the source code for the Boost standard libraries, you'll see why generics are not normally, it don't have to be a good thing. That being said, there are cases. As far as I know, it's still in the works. Maybe.
Awesome. Okay, so I think that's it for questions. Both Nicholas and Magno both say thank you for your questions. Oh, here we go, another one.
Very welcome.
Are there use cases that Go is particularly well suited for, or not well suited for?
So yes, so we tend to use Go a lot for anywhere you'd use C or C++. Go tends to fit in quite well. Some cases as well with Java, but not all cases. It's not particularly good for UI type work, but purely because the language support just isn't there. There is a WebASM compiler for Go, so you can pretty much write your JavaScript equivalents in Go. But because of the strict strong typing, you end up with a lot of code to do conversions in and out of the DOM. I've tried to do this and ended up falling back on JavaScript just because it's a better language that's suited for it. Anywhere that I'd write Python, I would probably tend to prefer writing Go, with the exception of anything that uses libraries like NumPy or Pandas. So for machine learning or heavy number crunching, just because, again, the library support in Python is so much better. Go is very fast. It's garbage collected. It looks different, but it's a very simple language in terms of structure. I very much appreciate the fact that every time I compile the code, like, by the way, when this is running the compilation in the Go, the play, it's not just compiling my code, it's compiling the entire standard library in milliseconds. It is extremely fast for that. So you get neat things like real-time feedback in your editor from the compiler. Yeah, hopefully that kind of gives you a flavor of it. I wouldn't write a mobile app in Go.
All right. Okay, so everyone's just saying thank you. It doesn't seem like we have any more questions just yet. Is there anything more that you'd like to just chat about, David?
So play.golang.org is the Go playground. And from the top there are links to tutorials, muck with the tutorials. If you race through them, you got a couple of hours of tutorial there. Get on board with the decisions that the Go language authors have made. Things like camel case is important. Tabs for indenting, which, whatever. Yeah, if you just suck it up and accept the decisions they've made, it turns out to be a very cool language, and it is generally a pleasure to write. So hopefully that's good enough.
David, you make it look easy. Thank you very much for your help today, David.
Very, very welcome.
I'm very thankful for your time. So is that it? Do you want to say anything more, or we'll wrap it up?
No, I'm good. All
right. So again, that is our second Google DSC lecture here for UQ. Hopefully we'll have David next time for an introduction to Google App Engine. We'll see how that goes. But yes, everyone, thank you very much for your time for joining today. And again, big thank you to David. It's been absolutely wonderful and truly wonderful to have an expert here in our midst. So, all right. Thanks again for everyone's time. Hope to see you next time. See you later, everyone.